Okay. So yeah. So this part is called quantum constraint anomaly. Okay. And this is basically some properties of previous defined quantum constraint operators. So let's firstly talk and recall our program, our procedure. So why we define those operators? So it's because we want to define some quantum constraint equations. And suppose we have a classical constraint, let's say a Hamiltonian constraint, and we want to quantize, get a quantum Hamiltonian constraint. I want this operator act on states and solve this quantum constraint equation. Yeah. So this equation is what we call quantum constraint equation. Okay. And similarly for diffeomorphism constraint, Cj, and this Cj is well, I mean, what we quantize is not our previous diffeomorphism constraint, but a little modified, as I discussed last time. And again, these should be, we have quantized these diffeomorphism constraint as operators. So in principle, we need to let these operator operating on states and solve this quantum constraint equation. Okay, and okay, and well, let's so first, this is called a this is at this moment we call this a naive proposal of solving constraints. Solving constraint, well, at quantum level. Okay, so from what I call it naive proposal. It means that this proposal definitely has some problems, and so it will be replaced by some proposal which is not very naive. Okay, and okay, so these are quantum constraint equation, and so we are going to look for solutions. Okay, and these solutions will be called psi. Yeah, and these solutions look for solutions, and these solutions will span span Hilbert space, because these equations, they are linear equations, because all those operators are linear operators, just like quantum mechanics. And when you solve those equations, you can see when you get a solution, and suppose you got two solutions, the linear combination of these two solutions are still solutions. So because these equations are linear, okay. And in the end, those solutions will span a Hilbert space. So firstly, a linear space, and well, and then this linear space will get some Hilbert space structure, the inner product from the mother Hilbert space, the earlier Hilbert space. Yeah, so in the end, and these solutions will span the Hilbert space, what we call a physical Hilbert space. Okay, and this is the goal of this procedure. And this physical Hilbert space is the goal of the procedure. Okay, and yeah, this is currently our proposal, and the reason why we make this quantization is following this proposal. But this proposal has problems. Obviously, has some problems. Yeah. So the most obvious problem is that usually those constraint equations are very hard to solve. Problem one. So the equations are hard to solve. Okay, the reason is that both operators, Hamiltonian constraint operator and diffeomorphism constraint operator, are complicated. Both, and how they are complicated is because they are both non-polynomial operators. Both of them are non-polynomial operators. So how to see they are non-polynomial? Well, the property of being non-polynomial coming from volume operator, because they both depend on volume operator. Depend on volume. Well, this volume operator is not a polynomial operator. This is a non-polynomial. Yeah? Because volume operator is Q operator squared and take 1/4. Yeah? So Q operator, this Q operator is polynomial, but well, you take square, it's still polynomial, but you take the power 1/4, it is not polynomial. Yeah, this is not a polynomial operator. So this volume operator is not a polynomial operator. Therefore, both Hamiltonian constraint and diffeomorphism constraint are not polynomial. Okay, but why it is so complicated? Because as we said, it is very difficult to diagonalize this volume operator analytically. Yeah, of course, you can numerically study case by case. Suppose you impose some spins in your spin network, and then you diagonalize your volume with respect to those spins by knowing those spins. Yeah, which means in that case you can diagonalize numerically, but to get a analytic diagonalization of this volume operator is very difficult. So that is one of the main reasons it is so difficult to compute diffeomorphism constraint and Hamiltonian constraint. Okay, so one needs so in principle, in order to do calculation, usually one needs to diagonalize q square analytic. You diagonalize this guy to compute, for example, matrix element of the volume. Because suppose you want to compute the matrix element of Hamiltonian constraint, and then firstly you need to compute the matrix element of the individual operators entering the Hamiltonian constraint. Yeah, and however, one of the operator is volume operator, but in order to compute the matrix element of this volume, you need to first diagonalize this Q, because this volume is defined to be this Q to the power 1/4. Yeah? So you have to first find the spectrum, find the eigenvalue, find the eigenstates of the Q operator, and then you take the 1/4 of the eigenvalue. Yeah? So that's definitely an intermediate step of computing matrix element of the volume. But as I said, diagonalizing Q is hard analytically. To diagonalize. Okay. Well, maybe your question is, although Q square is hard to be diagonalized analytically, but anyway, we can diagonalize numerically. So probably there are some numerical procedure to compute matrix elements or other quantities corresponding from the Hamiltonian constraint. Yeah, maybe one can compute, for example, numerically the Hamiltonian constraint and all the properties of Hamiltonian constraint numerically. Yeah, so this might be able, it might be possible, but as so far, there's no existing work on this. Yeah, yeah, there are several attempts, but it wasn't so successful. Okay, so it's hard to be diagonalized analytically, so it's hard to compute. C and CJ. Okay, and therefore solving constraint equations is even hard. Sorry, just a moment. Okay, sorry. Solving quantum constraint. Solving quantum constraint equation is even hard. Okay, so this is reason why firstly it is complicated to solve those equations. Right? All right. So yeah, so this is the first problem, and there is another problem, which is even more conceptually. Okay, so problem one it is more or less a practical problem, but problem two it is even a conceptual problem, and the problem two it is the most important part of this lecture, and the problem two is called quantum anomaly. Okay, so what is quantum anomaly? So remember that classically all those constraints are first class constraints. Yeah, namely, if you compute boson bracket of those constraints, it's still a linear combination of constraints. Yeah. So classically C and CA or CJ are first class. First class constraint. So more precisely, C and CA are first class. Well, CJ is just a linear combination of CA. So in the end, C and CJ are still are also first class constraints. Yeah. Okay, so they are all first class constraints. So I'm not going to repeat the constraint algebra specifically for Hamiltonian constraint, dimorphism constraint, but more or less C. So if I write Ci to be I index is both J index and index with no J, and also include the space time, the space points. So it corresponds to C of x and Cj of x. Yeah. So this is classical theory on the continuum. So here I it means J or X. Well, and also it includes the first constraint. Hamiltonian constraint has no J. Well, I mean, roughly speaking, J is something like J and X. And this index I is something like J and X. Okay, and then it being first class, it means that Ci boson bracket with Cj equals to Fijk Ck. Okay, so this means the constraint is first class, and also here this structure it is a structure function. Fijk is a structure function, so it depends on Q. It depends on the phase wave point. It's Fijk is a phase-based dependent function. Yeah, and Ci, Cj, Ck, of course, they are also phase-based dependent function. Okay, and okay, so now we have quantized those constraints. So the Poisson bracket should be replaced by commutators, and we should compute the commutation relation between those constraints and to see how those constraint algebra get quantized. Okay, and so suppose there are some possibility. Okay, so ideally speaking, if our quantization, so if we are really optimistic, and we may expect that our quantization gives commutation relations of constraints which are just well, replacing above Poisson brackets, yeah, just become naive replacement of above Poisson brackets. So if our quantization gives this will be the idealistic version of the quantization. Equals to F hat, okay, C hat. Okay, because all the quantities are phase-based dependent, and in the end, by the quantization, they are all operators. Okay, suppose our quantization gives this. This is really the most optimistic expectation. This is suppose. Yeah. Then then there wouldn't be any problem. Okay. Then what we can see from this relation is that everything becomes very consistent, and for any solution, and as I said, as our so from our procedure we get a solution, yeah, satisfying Ci psi equals to 0. Okay, for any I. Okay, and then because Ci operating on psi equals to 0, it gives the commutator of Ci Cj operating on psi equals to 0. Because well, Ci Cj both are operating on psi equals to 0, then yeah, of course, commutator, yeah, because this commutator equals to Ci Cj act on psi minus Cj Ci operating on psi, and these are 0 because psi is solving the constraint. Okay. Suppose we are able to find the solution. Okay, and so this is the first first equation, and secondly, let's say firstly, and but secondly, and we know that Fijk Ck. So these we compute commutation relation operating on psi is because of the left hand side of this equation. Yeah, it's become the left hand side of this equation. And suppose let's look at the right hand side of this equation operating on psi. Okay, and now this Ck contact with psi. Okay, and this equals to 0 again. Yeah. Okay, so therefore, suppose it means that our quantization is really consistent. Suppose we have this result. Suppose our quantization gives the commutation relation between constraint satisfying this relation. Okay, this is just a the result is just replacing above classical constraint algebra by the operator version. Okay, and suppose our quantization gives this result, and we let the left hand side of this equation operating on a solution of constraint equation, it equals to 0. Yeah, and the right hand side act on the solution of constraint equation, it also gives a 0. So we got 0 equals to 0, which is very much consistent. So this is all consistent. Okay, so it seems well, suppose we have our quantization leads to this constraint algebra at the quantum level, so then everything is fine. However, it is too optimistic. This expectation is too optimistic. So in the end, realistically, at most of the time, we don't have this constraint algebra, and especially more specifically in our previous quantization, the constraint algebra, the commutation relation of the constraints, is definitely not this. You got a lot of other terms in your commutator. However, this assumption is not really true. However, our quantization, and yeah, our quantization actually gives Ci, Cj. Well, of course, not equals to Fijk, Ck. Yeah. Well, what it actually equals to Fijk, Ck plus some correction, plus two kinds of corrections. So firstly, it plus some correction proportional to the lattice spacing mu, the coordinate lattice spacing mu, with some operator O1. And there is a second kind of correction, so which is proportional to H bar. Yeah, and the corresponding operator is O2. Okay, and so in the end, what we get is some relation of this kind of this type. And there are two kinds of corrections. So the first correction coming from discretization. Correction. And second correction is coming from quantum correction. Okay, and you can see that when we take the semi-classical limit and well, H bar goes to 0, and also taking the continuum limit and mu goes to 0, and we recover this classical commutation, classical Poisson bracket. Okay, so definitely it is the semi-classical limit is not really a problem for this commutation relation, but the result is not exactly this optimistic result. But you have to include two other terms. Well, these operator O1 and operator O2 may be also very complicated. It will be, well, it's a complicated operator. Okay, but in general, the formula should of this kind of this type. Yeah, should of this type. So when you compute the commutation relation, and it is not exactly the same as classical constraint